Let f of x equal e to the power of minus a half x squared. Show that the second derivative of f of x with respect to x is f double prime of x equals x squared minus 1 times e to the minus a half x squared. Well, we have to apply the chain rule here to get the derivative. The derivative of e to the power of something is just e to the power of whatever that something is. But then we must multiply by the derivative of the power. If we differentiate minus a half x squared, we get minus 1x. 2 times minus a half is minus 1, and we have x to the power of 1. And we can take that minus x in front of e to the minus a half x squared. Now let's look at the second derivative. We have to differentiate this function here. Now this is a product of functions, so we have to use the product rule. So we take one of the functions, say minus x, and multiply by the derivative of the second function. That's e to the minus a half x squared. So we have to differentiate e to the minus half x squared. But we've already done that. When we differentiate it, we get this. Then as part of the product rule, we add to it the function that we did not differentiate, which is e to the minus a half x squared, times the derivative of minus x, which is minus 1. So one function times the derivative of the other function, plus the other function times the derivative of the first function. That's essentially the product rule, u dv dx plus v du dx, if we call this u and this v. So we minus x by minus x plus x squared, and we have minus e to the minus a half x squared here. You see we can factorize out e to the minus a half x squared, and we can write this as x squared minus 1 times e to the minus a half x squared. The point P in the first quadrant is a point of inflection of the curve y equals e to the minus a half x squared. So this is actually the graph of y equals y equals e to the power of minus a half x squared. As a matter of fact, this is an example of the bell curve, or the normal distribution that's used in statistics. Normal distributions have the form e to a negative square, like it's minus a half x squared. Show that the tangent at P crosses the x-axis at 2, 0. So we want to determine this point here. P is a point of inflection of the curve. A point of inflection of a curve is a point on the curve where the curve goes from being concave down to being concave up, or if you like, from not holding water to holding water. See, it's curving up here, and it was curving down here. I've just exaggerated it. It doesn't hold water here, but it does hold water on this side. That's a loose definition of the point of inflection of a curve. It's also the point where the second derivative is 0, where the tangents go from, say, decreasing in slope to increasing in slope. As we move from left to right here, the tangents actually go from decreasing in slope, and as we pass through P, the tangents actually increase in slope. Well, the slopes become less negative actually as we move to the right from the point P. The tangents are approaching a horizontal line, which is a slope of 0. They're negative at P. So this is the point where the tangents go from increasing or decreasing to the opposite sense. So here is the second derivative that was worked out in the first part. We put it equal to 0. By solving it, we can actually find the x value of the point P. So let's solve this equation. So we have a product of two quantities equaling 0. The only way that can happen is if either of these is 0. So that means that either x squared minus 1 equals 0, or the other factor is 0. That's the only way you can get 0. One of these has to be 0. Now if x squared minus 1 is equal to 0, we have x equals the square root of plus 1. And that has two answers. It's either plus 1 or minus 1. So it appears that the x value of the point P is plus 1. As a matter of fact, minus 1 is the x value of the point of inflection on the other side of the curve. Now, what about this other factor? Well, this has no solution. The only way to get 0 is if we let x tend towards infinity. Then we'll have e to the power of negative infinity. E to the power of negative infinity is, if you like, 1 over e to the positive infinity, which is 0. So as x becomes infinitely big, e to the minus a half x squared will tend to 0. We do not say that infinity is a solution. Infinity is not a number. We don't think of that as a solution, so we ignore that. So we just say that there is no solution to that part. So this is the only part that interests us. So we found the x value of the point P, which is the point of inflection. So now we can go and get the y value of it. P is on the curve. It's on f of x equals e to the minus a half x squared. So we just need to get f of 1. So we just plug 1 into this and we get e to the power minus a half, which you can, if you like, write as 1 over e to the plus a half, which is 1 over the square root of e. So we found the coordinates of the point P. And what we need to do now is find where the tangent crosses the y-axis. So we need to get the equation of this tangent. We have a point on it. We also need the slope of it. If we have the point and the slope of this straight line, we can find out its equation and where it crosses the y-axis. To get the slope of a tangent to a curve, we get the derivative of the curve. So we get the derivative of this, which we've already done actually. We saw earlier that its derivative is minus x e to the minus a half x squared. We're just using the chain rule on this exponential function. So slope of the curve at P, which is also the slope of the tangent to the curve at P, is the derivative at x equals 1. So we just plug 1 into this and we get minus e to the power minus a half. So now we can get equation of tangent. So to get the equation of the tangent, we just have y minus the y value of P, which is e to the minus a half. I'll write it as 1 over root e maybe. No, I won't bother. I'll leave it as e to the minus a half. Y minus y1 equals m, the slope, which is minus e to the minus a half, times x minus x1, the x value of the point on the line, which is 1. So this is just y minus y1 equals m times x minus x1. x1, y1 is the point, and the slope m is minus e to the minus a half. So I won't bother simplifying this. All we have to do to find the y value of where the line crosses the y-axis is to notice that the x value of this point is 0. So we just let x equal 0. If we do that, we get y minus e to the minus a half equals minus e to the minus a half by minus 1. That's plus e to the minus a half. So we just plug 0 in for x. So then we can solve for y, because this is a point on the line. It has to satisfy the equation. So y equals e to the minus a half plus e to the minus a half. That's 2e to the minus a half. Actually, I've misread the question. We don't want this point. We want where the tangent crosses the x-axis, this point here. So how do we do that? Well, we note that the y value of this point is 0. Any point on the x-axis has y equal to 0. So we could just look at our equation and let y equal 0. That's straightforward enough. If we let y equal 0 and then solve for x, we'll have minus, well, if y is 0, then we would divide across by minus e to the minus a half. Minus e to the minus a half divided by minus e to the minus a half is plus 1. equals x minus 1. So that tells us that x must equal 2. So that's what we had to show actually. Not this point, but I've got it anyway. But this point here